Okay, so today we will start a new topic, namely radiation in participating media, and the first 15 minutes I will use PowerPoint because it is descriptive. I will make this available on Moodle, so you do not have to copy it down. After that we will switch over to regular chalk and talk. You will have to derive a lot of equations and solve problems and so on. So a participating media is an absorbing, emitting and a scattering medium. You know that any particle which has a temperature more than 0 Kelvin will emit, that comes from Provost's law. So it will emit. Absorption is something different for us. A gas volume absorbs radiation, that is if 100 watts per meter square come, what comes out may be less than will be less than 100 watts per meter square. It absorbs certain portion of certain electromagnetic radiation, so that is an absorption. So what it can do further is it can receive the radiation and reflect it in several directions, that is called scattering. Okay, from a volume we call it as scattering, this is called out scattering. Like that there can be in scattering from other directions also. So this out scattering need not be the same in all the directions, so which means it is not isotropic, it is anisotropic. There can be functions, that is this how much it scatters can be a function of theta, it could be f of theta, and then you will have to integrate what will be the total intensity of scattering and all that. So it becomes very advanced, handling scattering media and all that. So in this course we will avoid scattering, we will just have emission and absorption. Okay. So this is alright for unless you have big suspended particles and all that. If you have very small particles or no particles, but you still have carbon dioxide and water vapor, you can consider that to be just an absorbing and emitting media. So the study of heat transfer through media that can absorb, emit and scatter radiation has been receiving increased attention in the last 40-50 years, and this subject was not there before 1940 or 1950. In fact, it gained momentum and Professor Subramaniam Chandrasekhar actually figured out the equation of radiative transfer, Nobel laureate physicist from India. So early work probably in the 30s and 40s. Afterwards engineers started looking at it because it had a lot of engineering applications. I will let you know. The interest arises from phenomena associated with rocket propulsion, combustion chambers, ablating systems, nuclear fusion and insulating systems. In all these cases you have gases which are participating, gases which are not like air. In this room radiation from the left wall will directly go to the right wall, the air will not participate. Air is at temperature, is at some temperature, convection may take place, all that is okay, but this will not create mischief. But if the moment you put carbon dioxide or water vapor, it will do something, it will absorb and then something it will scatter and all this. That is why we have this global warming, greenhouse gases and all that, because they will not keep quiet, and their absorption and emission and all that is spectrally dependent. Okay, if it is spectrally dependent, that means it has to be dependent on the temperature. And if you look at the absorption of solar radiation by the earth, you can see that the radiation is incoming from a black body at 6000 Kelvin, whereas the outgoing radiation is from a body at 300 Kelvin or 288, you worked out in the quiz, you worked out the earth's temperature. So basically the incoming is mostly in the visible, outgoing is mostly in the infrared, and if the gases which are in the atmosphere are such that they permit the incoming and do not permit the outgoing, okay, then what happens is there is a constant build up of energy within the earth. This is responsible. This is a very quick half a minute course on global warming. We can actually work out the spectral bands and all that and find out if the concentration of carbon dioxide in the atmosphere is increased from 380 ppm to 390 ppm, what happens and so on. We can do detailed calculations, spectral calculations like what we did yesterday. We did spectral radiosity, like that you can find out for the atmosphere and so on. So there are lots of engineering applications for gas radiation. So some of these are new, but some are over 100 years old. The earliest of phenomena man was interested was in atmospheric radiation. Astrophysicists have also been interested by gas radiation with regard to studying the stellar structure, right. If you want to study the structure of stars, you have to find out the radiation which is coming out from the stars. You will have instruments, you will have Hubble telescope and all that, and then you get some radiation, then you use some equations and then figure out what is going on. This kind of activity is basically of fascination to astrophysicists. That's the kind of work they do. So they analyze the spectrum coming from various stars, other planets and all that. The spectrum observed during emission or absorption of radiation by a gas is characteristic only of that gas. Okay, from the spectrum you can get what is the signature. Okay, that is a signature, we all put signature. That means you are saying that if I say Balaji, if I sign, that means I have seen it, I have read it, it is me. like that. If you say Vikram, like that, this suppose you get a emission spectrum from a gas, from the gas which is surrounding the, which is at the surface of a planet or a star, then it is indicative, it is diagnostic of what is the gas which is present on that surface. So from that we can figure out many things. Then if you study over various periods of time, you can find out the gas concentration which is changing, and then you can put some equations, you can figure out whether that star is moving away from us, whether it is moving closer. They will do all sorts of, they will apply some mathematical models, they will combine their experimental data with mathematical models, do such type of work. Hence this spectrum can be used as a diagnostic tool to determine the gas temperature and concentration. Okay, like that we have all these techniques. You go to sophisticated analytical instrumentations and facilities, SAFE, which we have here, cell scanning, electron microscopy, X-ray diffraction, based on some physical principle, it will give you some output. From that output is called the signature of that specimen, or somebody is doing ultrasonic, and then you can get the structural health of something by remotely finding out, send some ultrasonic waves, get the echo pattern. You send the echo into the abdomen and send the signal, receive the echo, and find out. It can even tell us whether liver cancer is there, pancreatic cancer is there, and all that. That is, so that gives the signature of what is going on in the, what is the texture, what is the echogenicity, what is the texture of this thing, the tissues in the liver, whether it is normal or it is suggestive of carcinoma or something like that. Like that, these spectrum can also be diagnostic of the gas temperature and then concentration. Okay, so if you consider a black body source, stellar means star, okay, star core, so or a diffuse gas, example outer layers of a star structure, you can look at two spectra, you can look at the emission spectra or the absorption spectra, and give a signature like this, intensity versus wavelength, intensity versus wavelength. From this you can figure out what will be the gas concentration, gas temperature. So this is basically what is called as an inverse problem. From the output you will have to figure out the input. So there can be various causes for this spectrum. So the goal of a successful inverse methodology is to correctly identify the cause which led to that behavior. Okay, so these are discrete spectra, these two, this is a continuous spectrum, this is just a depiction. Okay, okay, simplified representation, you have a hot source, there is a gas, and then you can either get a continuous spectrum or you can get a absorption spectrum like this, emission spectrum. These are called absorption bands, these are called emission bands. Okay, if you look at the incident solar energy flux which is coming on to the earth, then you can see, so this is basically EB lambda, watts per meter square per micrometer versus lambda. Now this first line, dashed line, gives the energy distribution for a black body at 6000 Kelvin. Now this is the actual solar radiance outside the atmosphere. Okay, so then solar irradiance after passing normally through the atmosphere. Now you can see that it has got a zigzag variation, because mostly there are absorption bands available, oxygen molecule, right, diatomic, triatomic, oxygen, water vapor, and all this, carbon dioxide bands. Because of this there is a signature. Okay, so you can actually figure out the concentration by having an instrument which will have a sensor which will capture within two particular wavelengths and so on. So you can see that ozone is very much, this ozone absorption is there very much in which part of the spectrum? This carbon dioxide, infrared. Okay, this water is everywhere, that is why this water vapor, you can design an instrument to measure the water vapor by having a multiple channels. In a geostationary orbit you can put a satellite, so it is called a multispectral, it's called a multispectral instrument. Okay, it's called a multispectral sounder. So the INSAT series of this thing, for which we are also working, next one is INSAT 3D series, which will have 18 channel. We basically want to look at, we basically want to get the water vapor and temperature profile, water vapor and humidity. Okay, so we are actually coming out, so the launch will be anytime this year. In passive remote sensing, the radiation emitted from the earth's surface, which is absorbed and scattered by the atmospheric constituents, is measured at the top of the satellite, it is called a top of the atmosphere radiance. The radiation emerging out of the atmosphere can be measured through radiometric sensors placed on satellites. It could either be polar or geostationary. The intensity itself is a matrix consisting of spectral intensities, that is you can measure it at, just like yesterday we saw with various j lambdas, you can get the j lambda or the q lambda as a function of lambda. It will not be as a function of lambda, it will be at discrete values of lambda. The inverse problem of radiative heat transfer is concerned with what are the atmospheric constituents which gave rise to this q lambda at various lambda. So what will be the logic? You will assume some atmospheric concentration, solve the equation of transfer and find out q lambda at various spectral at various lambdas. You will match your prediction with what is observed by satellite. Generally it will not agree, then you will iterate, you will give a new guess, you will keep on guessing till they match closely. So this guessing is easier said than done. What I told you in one word as guessing is the field of inverse problems. Okay, how do you scientifically guess? That is inverse problem. There are so many things, Bayesian inference, Markov chain, Monte Carlo, hybrid Monte Carlo, so many regularization, Tikhonov regularization. So whole big field of inverse heat transfer is there. Okay, there are journals specifically devoted to inverse problems in science and engineering. There is one journal. Okay, what about gas radiation in industry? Gas radiation finds application in furnaces, carbon dioxide and water vapor or combustion products. They are significant emitters and absorbers. These gases are found in furnaces, combustion chambers, IC engine. They are also there in IC engine. Okay, gas radiation is also important in IC engine where the flame temperature can reach a few thousand Kelvin. Also the one important thing is there is also soot. Okay, there is also soot in the IC engine products of combustion. Soot also is luminous. Okay, so soot also contributes to gas radiation. How do you handle soot? So some group of scientists have worked soot modeling. That is another separate field. There are some big stalwarts in Chalmers University, Sweden and all that, where whole lifetime they have done soot modeling. Whole lifetime they wrote lot of things. All your commercial codes, all the codes will use this. The moment they are found to be inaccurate, somebody's code is found to be more accurate, that will be incorporated. That is how science and technology progress. So if the origin of all this is basically the classical problem of radiation from molten glass in a furnace. So glass making is glass blowing is basically a very traditional and very old technique. So temperature distribution in molten glass, when they measured it, they found it to be more uniform than expected from heat conduction alone. When they did the measurements, when they solved the heat conduction equation, if there is a theoretically expected temperature distribution, the actual temperature distribution was much more uniform. Then they started investigating why is it like this, why is the conduction equation not able to satisfy this accurately. Then they thought that convection is the culprit. There may be some convection at the boundary, then you put Q is equal to HA delta T minus K dt by dx is HA delta T at the boundary and all that. They could not get agreement. Finally they found out within the glass itself has got an emission and absorption characteristics, and therefore you have to integrate this conduction with the equation of transfer. Okay. So in the late 40s it became clear that gas radiation was responsible for the observation. So when radiation interacts with the substance, part of the energy may be redirected by scattering. Scattering can be caused even by an electron, or it can be caused by a planet also. So these are the length scales which are involved in scattering. Depending upon the length scale, I will use different theories of scattering. If it is very small, I will use only Rayleigh scattering. Rayleigh scattering is studied by Raman, and that's why the sky is blue and all that. Next, if I have ice, water, rain in the atmosphere, I can't use Rayleigh scattering. I will use what is called the Lorentz-Mean. I will use the Lorentz-Mean scattering theory. That is what we do in our work. A little more advanced, after some level, if the particles are big enough and they are non-spherical, big ice particles, then all these theories will fail, because Lorentz-Mean scattering basically assumes the particles to be spherical. Then all these will cup. Then you have to use geometric optics. Finally, it will become optics, electromagnetic theory of optics. That is the escalating difficulty level associated with studying gas radiation. What are the principal difficulties in studying gas radiation? Everything is happening from a volume, it is not happening from a surface like before. Everything is happening from a volume, and as usual the problem is there. This absorption, emission and scattering, they are function of lambda. that is also there. Okay. So absorption, emitting and scattering happen not only at the system boundary but at locations within the medium, which makes it mathematically very difficult. Azimuthal, zenith, all angles have to be considered, and this fellow may behave differently, it may behave crazily in different directions, though these have to be accounted. Spectral effects are more pronounced in gases than from solid surfaces. This grey gas assumption is more a myth than a reality, but many surfaces we put grey diffuse and proceeded, isn't it, in the last 1 month. Hence the engineering treatment of gas radiation. However, as engineers we want to solve the problem, we do not want to simply say the problem is very difficult and keep quiet. We want to make some products and okay. So we want some approximate solution. Therefore, the engineering treatment of gas radiation would involve simplification of one or both of these difficulties. What will I say? One I can say that scattering is negligible, that means I am handling 0.1, or I will say that in the region of in the spectral region of interest it is grey. So I will do one or both of the simplifications in order to make the problem tractable. Okay. Now, what are the important properties for study of gas radiation? Kappa lambda. Kappa lambda is the monochromatic or spectral absorption coefficient. Kappa is the absorption coefficient. Therefore, if incident monochromatic radiation is given by I lambda, the absorption by the gas per unit volume, per unit solid angle, per unit wavelength interval is given by I lambda kappa lambda. Okay. Watch this, watts per meter cube per micrometer per steradian. We used to get watts per meter square per micrometer per steradian for radiation from surfaces. So if it is watts per, so that watt per meter cube is there, and kappa is not dimensionless. Kappa is not dimensionless, it has the units of meter minus 1. Similarly, we have an epsilon lambda, which is a monochromatic or spectral emission coefficient, which also has the units of meter minus 1. So the epsilon lambda we define for gas radiation is different from the epsilon lambda we define for the radiation from surfaces, right. Now, okay, the emission by the gas per unit volume per unit wavelength is, so this is absorption. Emission is basically watts per meter square per micrometer per steradian into 1 by meter. It is also watts per meter square, sorry, watts per meter cube per micrometer per steradian. Now we will move on to the equation of transfer. There is a short form from also known as, right? Huh? No, that is okay. There is a short form for also known as okay, AKA. Okay, so we are not worried about the short form of AKA. The long form of RTE. The long form of RTE is radiative transfer equation. So S. Chandrasekhar is credited with this mathematical development associated with the equation of transfer, and it's a brilliant book. It's very difficult to follow beyond 10 for the first 10 pages. It is there in the library. Principles of radiation or radiation heat transfer, or his mathematical level is so high. So S. Chandrasekhar, right? Our Indian scientist who studied in Presidency College, Madras, near the beach. he did his BSc physics there. Okay, so his book is there, is all is, so every 10 years he used to change fields, radiative transfer, stellar structures 10 years, hydrodynamics 10 years, every 10 years he will conquer a subject, write a book and move on. Okay, and he says, he said that the greatest invention of mankind is God. So you can find out his leanings. Okay, that is what he said. Okay, now let us this is our gas volume, cross sectional area is dA, this is ds, okay, radiation is I lambda at S, I lambda at S plus ds. Okay, radiation in traveling in this direction, generally the direction is S. Okay, Cartesian coordinate system we can just later on replace the S by X and so on. In order to make it less restrictive, we can use the notation S. Okay. So some I lambda is coming and it is going out. Okay, so it is basically going through a distance ds. Okay, the area dA is normal to the direction S. Okay, the radiation is traveling in a direction normal to the area. Okay, now we are trying to find out what is the rate of change of this intensity, what is the rate of change of the intensity of the radiation when it is passing through this gas volume. That we can write it using calculus, dA by d lambda whatever. Then we have to find out this rate of change of intensity not being equal to 0 is because of what all factors. We are neglecting scattering, there could be only two things. There could be absorption within the gas volume and there could be re-emission from the gas volume. So the balance between emission and absorption will lead to this di lambda. If you write this equation, write these three steps, that is the equation of transfer. And it looks like it is innocuous, it looks like a very simple, very unassuming equation, but that it is we cannot say it is innocuous, it is deceptively innocuous, because when you have to solve it for a 3-dimensional case, it becomes extremely formidable and difficult to solve. Okay. Now let us say, so let us consider change of intensity when passing through the gas volume is I lambda S plus ds into I lambda has got the units of so we have to multiply by dA, do not multiply by dA ds, okay, dA minus, correct, what is going out minus what is coming in. Using a Taylor series expansion, how will you write this? di lambda by ds okay, plus higher order term, So we set the higher order terms to 0. That is the error associated with this approximation. If the ds is very small, this approximation is alright. Now energy absorbed by the gas. Please be reminded that it is a spectral formulation. I am retaining by watts, I am retaining the watts per micrometer per steradian, it is a spectral formula. Okay. So what will this be? I introduced two important properties, kappa lambda and epsilon lambda. So please tell me, kappa lambda, I lambda multiplied by dA very good. D lambda is anywhere there, no, it is there in I lambda itself. Okay, 2. We looked at energy absorbed, we also look at energy emitted by the gas volume. Will be epsilon lambda not I lambda, come on. IB lambda of Tg, very good. Tg is the gas temperature. The intensity I lambda need not be related just to Tg, intensity I lambda is coming into the gas volume, it can be from somewhere else, but what it emits will be completely dependent on its temperature, correct. So epsilon lambda, no, do not leave the other things, into dA ds. Both are additive, which increases the I lambda, which decreases the I lambda.
I lambda increases with epsilon lambda and decreases with kappa lambda.
Yeah, with the absorption the I lambda will tend to decrease as the radiation passes through the gas volume, but this will be compensated by the emission from the gas. Therefore, if you have to do this, if you have to do an energy balance, this dI lambda by ds will be equal to this minus this, correct. Okay. Now performing an energy balance. You can cancel dA ds throughout. Correct. When you cancel dA ds throughout, it is implicit that dA into ds cannot be 0. Therefore, these equations are not valid at mathematical points. That is a control volume. A mathematical point has no area, no volume, nothing. So these are valid only around a small area or volume. That's very important for us. Okay, all right. Otherwise, you are not authorized to do that. Then you can take that 4. How do you prove 4 equal to 6? 4 into 0 equal to 6 equals 0 into 6 into 0. Therefore, LH is equal to R. What is that? No, you tell me. When it is absorbing, I am saying that I lambda will decrease. Okay, I have a sheet of water, I am shining radiation on this. Obviously, as the radiation goes through, the bottom layers will get less radiation. In that case, what will happen to I lambda from the surface? It will exponentially decay. Correct? So it decreases the intensity which is coming out because some of it is absorbed. If 100 enter, 95 comes out, 5 is held back. But that 95 can be compensated by it can become 97, 98 or even 105 if there is an emission from that gas. Correct? What is that? That is a change, yes. Okay. Now therefore, no, some people want to write it like this. Yeah, any problem? This is the RTE equation, RTE, this is the so called radiative transfer equation. Yeah, you have to have in-scattering and out-scattering. So dI lambda will be equal to, dI lambda by ds will be equal to emission minus absorption plus out-scattering minus out-scattering minus in-scattering, that we will take care of the algebraic. But this out-scattering in-scattering also will involve some integral terms, because this scattering may have integration which is different in different angles. Correct? If you include scattering, you may have to use an integral term, because integral with respect to that solid angle, because it can scatter differently in different directions. Then what will happen is the left hand side will have differential term and the right hand side will have integral term, then it will become an integro differential equation. The classic radiation equation is an integro differential equation. Already differential equation is so difficult to solve, integral equations also are very difficult to solve. So the integro differential equation make the radiative heat transfer extremely difficult. Fortunately, we have numerical techniques and methods now available. People struggled. You please look at the book Methods of Applied Maths by Hildebrand. They have variables, separable kernel and all that, they have kernel of integration, and so it was considered a big craft solving an integral equation. I did not tell you the integral equation at all, I just quietly moved on. Okay. Suppose we consider a 3 surface enclosure in which the temperature of each of the surfaces is varying with respect to x, and I can't use the uniform radiosity assumption. If I cannot use the uniform radiosity assumption, I have to divide each surface into subparts, and then I will have jx dx, or j1 itself will have several things. Therefore, instead of summation I have to use that integral. Therefore, the radiosity equation which I told you, where I put j equal to epsilon sigma t to the power of 4 plus 1 minus epsilon sigma fij jj will be integral. So the radiosity equations per se or by themselves are integral equations. I did not want you to get scared. So when I learned it as a student, Professor SPV taught me all this integral equation. Exam questions were there, that integral, how to solve kernel. There are 2 types of integral equations, integral equation first kind, second kind, Volterra integral, Fredholm integral. There is a separate field. I do not teach my students all this now. You can straight away put sigma and use the Gauss-Seidel method and proceed. Okay. So radiation is very deadly. Okay. Now are you happy with this equation? Okay, it is fine, it gives you the rate of change of this thing, blah blah whatever, but I am having 2 properties. We try to do something where we relate the properties, right. Previously we tried to cut down the number of properties we want to independently evaluate. Can we do something like this? So I will do a small trick. Let the gas be contained in an isothermal enclosure. I will put forward an argument like this. Let the whole gas let the whole gas be in an isothermal enclosure. Then what is the story now? At is it correct? What is the funda involved in an isothermal enclosure? Gas and wall all are at Tg. I lambda, anywhere at any point will the radiation be the same? Is it an isotropic radiation? Even if it is not black, the it's multiple internal reflection. So the I lambda is not a function of S. If I lambda is not a function of S, what is di lambda by ds? Dhaval, you are not following. What I am saying is, if okay, it is isothermal everywhere, okay, then it is like if you put a hole, radiation coming out will be analogous to radiation coming out from a black body. So you got more or less a hole drum or a black body here. Therefore, if I take a sample, if I take a gas volume and find out its I lambda in a particular wavelength interval, if you take it here, will it be different? Okay. Therefore, di lambda by ds equal to 0 anywhere within the isothermal cavity. What additional simplifications we can make? And I lambda will be equal to I lambda will itself be equal to IB lambda at Tg, correct. Therefore, 0 equal to no. In simple English, epsilon lambda equal to what was this law? Kirchhoff's law, correct. We already know this, but I try to derive it from first principles because you may object, sir, previously epsilon and alpha were dimensionless, now they are having meter minus 1, how do you prove? Now somebody will ask, sir, if it is not an isothermal enclosure, will it be valid? Or I have used that isothermal enclosure concept only to get the relationship, it is universally applicable. You can make measurements and check it, okay. Now therefore, no. Okay. This is the RT equation. No way. Di lambda by ds, correct? Did I make more mistakes? Yeah, it's okay. Don't assume that this equation is for the isothermal cavity. Isothermal cavity there is no RT, man. Isothermal cavity I lambda is constant everywhere. Why do you solve RT? You solve an RT, you write an RT and solve it because I lambda is changing. We want to find out what happens to I lambda when it goes through some gas volume, right. So you can see it is formidable. Hey, it looks so simple, sir, it is only di lambda, it is after all ordinary differential equation and note now when you actually the next class you will see the mathematics which comes out of it. It will lead to something, it will lead to an integral which cannot be evaluated. And then people invented what is called the exponential integral function. This simple equation will lead to so many complications that we will see in Wednesday's class, okay. But before that I want to give you a sneak peek into what happens when the absorption is much more important than the emission. Okay. So let us consider a case. I will look at an asymptotic case. We still have 5 minutes. So let us consider a wall. Okay, let us consider a wall which is black, it is at a temperature Tw, then it is surrounded by this, there is this gas at Tg, okay, this radiation is coming out of the wall, okay. So the radiation which is falling on, let us say I have a receiver or a receptor, the radiation falling on this which is at a length L will depend on two things, or it is made up of two contributions. What are these two contributions? The first contribution is the radiation from the wall which is given by sigma Tw to the power of 4 by pi, okay, that is I lambda, that is I. So I lambda, so the sigma T to the power of 4 by pi which is originating from the wall, which is modified or attenuated by the presence of this participating media and which eventually reaches this. That is not the only radiation which is arriving at this, there is also the radiation from the gas which is arriving at this. But what will happen is the radiation falling on this can also arise from this portion of this wall, so it could be at an angle. So we have to derive the formulation for a general angle theta, and then when theta is equal to 0 it is for the normal angle, okay. Now slowly I am introducing the complications, we will work this out in the next class, but now I want to look at this simplified case. When Tw is much greater than Tg, what happens to the equation? Which term can be neglected? The epsilon lambda Ib lambda Tg is much smaller compared to the other terms in the equation, because the emission component is very less, okay. I have a 1000 Kelvin wall and the gas is only at 300 Kelvin, okay. When RT becomes I will say that this is x direction, and I will say uh, 10, therefore okay, assuming a grey gas, so if we integrate I equal to correct. So the radiation decays exponentially as it passes through the depth, okay. So this is called the This is called the Beer's law or the Beer-Lambert's law or the Lambert's law. So, the solar radiation which is impinging on the ocean waters. So, let us say it is I naught at the surface of the water, then as it goes it will be I naught into e to the power of minus kappa x. So, as you go to the bottom layers of the ocean, the radiation which is received at the bottom layers of the ocean is much less compared to whatever is received at the top. Because the radiation received at the bottom is much less, the bottom layers are at a temperature which is lower than the top layer. Therefore, the top layer will be at 30 degrees, the bottom layers, the temperature, for example, at 1 kilometer it may be something like 1 kilometer depth, it may be something like 10 degrees centigrade, okay. And then this is a stable temperature gradient because the warmer and lighter water stays at the top. This is also responsible for maintenance of aquatic life and all that. And then if you exploit this temperature difference, you have what is called the ocean thermal energy conversion called OTEC, okay. And you can see that it is very difficult for organisms to survive deep below because no light is not available for photosynthesis, okay. So, some simple radiative transfer equation can be used to explain so many phenomena, okay. But this is because the radiation is coming from black body at 5800, you do not worry about epsilon lambda IB lambda of Tg because that is only ocean temperature, is about 300 Kelvin or something, okay. But in the general case, when the gas emission cannot be neglected, then we are in trouble, then the integration becomes very difficult if you want to evaluate the heat flux. I will introduce the exponential integral function, I will give you tables and you have to use these tables to compute the heat fluxes, okay.